move your computer.
I don't know. I don't even know if that's how much student government sent me. I feel like student government sends me the stupid schedule every day, and I missed it.
Charging us $75 a year.
They send you the same thing every day. Why keep checking it?
Exactly. Okay. You ready? How was math test?
What test?
Someone at the bottom.
Hello.
Okay, so where we left off, we understood NMR at some level.
Did we?
I don't know. Well, maybe for some people.
On the y-axis, we had intensity, and in a lot of ways, you could read that as the relative number of hydrogens. So if you have more hydrogens of a type, you would have a peak that was taller. And so one more time, we talked about how the super cool kids might recall that tetramethylsilane is our most favorite internal standard. And largely that's because it has 12 identical hydrogens. And so you can imagine that the intensity of the peak would be good and tall, because there are 12 of them. And so even a very small amount will show up and allow me to put a 0 on my spectrum. The axis on the bottom is not intensity or number of hydrogens, it's chemical shift. And chemical shift is measured in parts per million, where we're measuring the difference in the frequency of the spin flip that you have to that of this particular molecule. So as things go this way, we refer to them as increasingly shifted. And just to keep you on your toes, we call the things over here quite well shielded. So shifted and shielded are antonyms of each other. What shields you in an NMR? The electrons.
That's why you can't have magnets in an MRI machine.
So we also learned that you could consider electronegativity as sort of a way of deciding how shielded or shifted you might be. So if you had this molecule, my expectation would be that this hydrogen, which is on a carbon that has 2 chlorines, is going to have less electron density.
Gotcha.
So it is going to be more shifted.
Okay.
While these have more electron density, and consequently would of course be less shifted, more shielded. Or if I drew this in a cartoony kind of way, I would expect that methyl group to appear around 1 to 2 parts per million, and I would expect that other thing to occur around maybe 5 parts per million. And I would expect the relative intensities of those to appear in a 3-to-1 ratio.
Are you pointing at the hydrogens or the carbons?
I'm pointing only at hydrogens. All I can see here are hydrogens. Good question.
And again, it's less electron density, the hydrogen there because the chlorines.
Yes, the chlorines are suckling it away from the carbon, which in turn is pulling it away from the hydrogen.
So that one hydrogen is at the 5, and the 3 other hydrogens are at the 1 to 2. Gotcha. 3-to-1 ratio.
Do you agree this is where we were last time?
I agree.
So the number of peaks was the number of distinct chemical environments. The integrated area under the peak, or the height of the peak, depending on how I draw them, is the number of hydrogens. So here they're just simple lines or delta functions. So here I could measure this one, and it would be 3 times as tall as this one. But if they actually had like some shape to them, then sometimes you'll see like a little integration sign drawn over it. What? The integration sign is showing me the area underneath this peak. And so I can actually use a ruler and measure this in centimeters, measure this in centimeters, and expect that I will find a 3-to-1 ratio. Sometimes it's very obvious, other times they have to draw this picture because you can't tell what's wider than what. So number of environments, number of hydrogens. So the last thing that we need to learn about is the structure inside these peaks. So let me show you what I mean in a picture. I hope you can see that this peak isn't actually one line, but in fact it's made up of 3 lines. We'll call that a triplet. Or this is not actually one line, it's in fact made up of 4 lines. We'll call that a quartet. So I want to understand why this looks like a quartet. I want to understand why the intensity within the quartet is 1 to 3 to 3 to 1, while the intensity within the triplet is 1 to 2 to 1. I want to understand that. And I want to know if this is enough to build a whole molecule. God, I hope it is. Okay, so this last effect is called spin-spin or J-coupling. It's not the only kind of coupling you'll see, but it's the only kind of coupling we'll talk about. I'm sure you'll be disappointed. The idea is that hydrogens, hydrogens that are on your carbon, or hydrogens that are, hydrogens that are on your carbon, or hydrogens that are symmetrically the same as you, equivalent to you, won't affect you. But hydrogens on other carbons, hydrogens that are different from you, are little magnets. That's why we've been seeing these flips, because we know that the magnet can be, with the applied magnetic field or against it, but each one of those hydrogens is a little magnet. And that means that if those magnets nearby are oriented with the field, then locally you'll experience a higher field. If they're against the field, then you'll experience a somewhat lower field. And if they're like ambiguous, you'll just experience exactly the field that I applied. Ooh, the faces are bad. Simplest example. Okay, I got 2 carbons, and on these 2 carbons are 2 hydrogens. I called them A and B, so you could check them out. And the first thing I want you to notice about A and B is that they are 1, 2, 3 bonds away from each other. So for this effect to arise, we need to have 2 hydrogens that are 3 bonds away from each other that are not equivalent. They are not the same as each other. A and B are distinct. That's why they have different names. Oh, someone's at the door. I heard. See the board. Thank you, Clint. I'm sorry.
How late you got here?
Okay, so what I tried to say that got a lot of blank looks is that the spin of A could be aligned with or opposed to, the external field. If it's aligned with the field, Brecken's not only going to feel the field, but he's also going to feel the little tiny proton. It's going to be bigger. That means that when Brecken flips, it will take a little bit more energy. You might recall, I like this picture a lot. We had the strength of the field increasing. This is what it would cost Brecken to flip, given what I think I'm applying. But now I realize that sometimes a little magnet next to him is pointed along the field, adding to it, and so he's going to flip at a higher energy. And other times, the little magnet here is opposed to the field. So we're gonna take the big field, we're gonna subtract a little tiny field, and we're gonna find that Brecken flips at a slightly lower frequency. So when Brecken decides how to flip, he's actually not gonna appear where I thought he would. He will appear a little bit higher, or a little bit lower. There will be two signals of Brecken showing that I, his neighbor, can be with or against the field. So if Brecken has one neighbor, he will appear as a doublet. Anything that appears as a doublet has exactly one neighbor. Let's see if my witticisms help. Okay, so this is A talking, I presume. He says, hey B, if you align with the magnetic field, I will feel a stronger field. If you oppose the field, I will feel a weaker field. That means there will be two frequencies that are resonant with my spin flip. So the two frequencies are the frequencies I've drawn in black and brown. The one in black is when the neighbor was aligned with the field, so the magnetic field experience was a little bit stronger. And the one in brown was when the little magnet neighbor was opposed to the field, so the field he experienced was a little bit weaker. So the fact that he has a neighbor means that he's going to appear differently.
Wait, so the original hydrogen experience is both, or like at the same time, or like one at a time? Like, is it like, I'm confused.
So there are a lot of molecules in there, right? When we're talking about moles of things, we're talking about 10 to the 23rd of them. So there are a lot of molecules in there. And so I'm going to see a signal in my NMR that is the signal of all of these molecules at the same time. So when one molecule, the type of hydrogen that Brecken is, has a neighbor that's with the fields, so Brecken's going to show up at this resonance frequency.
Okay.
But in another molecule, it will be opposed to the field, and so he'll show up with this frequency. All I can see is that there are two frequencies, and those of you who are astute or have, extremely good photographic style memories will notice that, like, this is a little bit taller than that. Like, there is a little bit of statistics in here, but we're not gonna go down that gross path.
Why is when it close, like, it takes less energy?
So when it opposes the field of the little proton magnet is oriented in the opposite direction as the field of me. And so what Brecken sees is the sum of these two things. So he doesn't see the full applied field, he sees the full applied field minus this much. So it'll be easier for him to flip.
So in a way, like the neighbor thing is shielding it,
But it could be unshielding it, right? Because it goes either way. It can make it bigger or smaller, so it's affecting it, yes.
So, like, okay, this is like one of the things, right? And this is another one, this is like the neighbor, right? And this is the magnetic field. If these two are aligned, then this would feel the magnetic field stronger. But if this was like opposing the magnetic field, it would feel weaker. And what does that have to do with like this spin?
So we're always looking at how much energy it takes to flip a spin, and we know that's proportional to the strength of the magnetic field. So if Brecken is not just feeling the applied field, but he's feeling the applied field plus, he's going to have a flip at higher energy. If he's feeling the applied field minus, he's going to have a flip at lower energy.
And
The middle of these two things is where you and I would have expected it last class, but we're seeing that we'll see two distinct peaks.
so the one where it requires less is the y-axis intensity or energy.
The y-axis on this is energy.
So in the case that it would require less energy, so the brown, would that be if it is aligned?
Against, so this field is making me smaller.
So because it feels the weaker magnetic field.
It's easier to flip.
So I remember the last time you had like that big NS magnet on the side.
Yes.
Because it was like super strong.
Yes, that's what I'm trying to make my body, the big NS magnet. And my finger is a little tiny proton that can point with or against.
Okay. And in the case of it points against, it's gonna decrease because it like takes kind of the vertical.
Yeah,
And what's that concept called? Is it?
spin coupling or J coupling. I call it spin coupling. If they're both B, there's no effect, you don't see this.
No effect.
So if you put ethane into an NMR, where all 6 of the hydrogens are the same, you'll see a singular peak.
Okay.
But if you put bromoethane into that NMR, then we're gonna say these 2 hydrogens see those 3 hydrogens, and these 3 hydrogens see those 2 hydrogens. Oh my God, what is that gonna do? Don't worry, we'll get there in a minute. You cannot split yourself. You cannot split yourself. So a B cannot split a B. Only an A can split a B. The 2 protons must be different. You cannot split yourself.
When would the spin change?
When the radio frequency is resonant with the spin flip.
What? Wait, so that what?
I didn't understand the question either, if
Like,
that's any
you
good.
know- You know how like the spin changes from the low energy spin state to the high? When does that happen? Like, does it just happen like that?
No, it's like when you apply like the radio waves.
So there are radio waves shining on this, and so when you absorb a radio wave, that's when you flip. I think you're coming to another problem that's fair. How much energy is in the room right now? It's a weird question. It's kind of a lot, because we're at room temperature. And so the energy is proportional to the temperature. That's like kinetic molecular theory, the energy is proportional to KT. And so, while I would live in a world of DT if I could, where everything was in the ground state, and it only got to be excited if I shine the light on it, what I feel like Moheb is considering is that at room temperature, more molecules will be in the ground state than the excited state, more nuclei will be in the ground state than the excited state, but some of them will be in each. We will see the flip, as Amarachi said, when it absorbs the radio wave. But there are a lot of magnets in this state and a lot of magnets in this state, though there is a majority, it's like 1 in 10,000 extra in this state. So it's almost statistically even. It's a little bit offset. Sometimes you can see that offset in the NMR, but I think that's going down a rabbit hole I don't know that you want to go down. Boltzmann statistics.
A can't flip an A either.
So A will not have this coupling with A. A will not couple with A. A will not, I'll say split, that's fine, A. Okay, so I have 2 spins. I have a hydrogen on this carbon with 2 chlorines. I have a hydrogen on this carbon with 2 bromines. They are not equivalent. They are A and B.
How would we know? How would you look at that?
Not equivalent? Because to be equivalent, they have to be like symmetrically the same, and I know chlorine and bromine aren't the same.
But they're both, they're different.
They're different what?
They're both,
Halogens?
halogens, right?
Yes, but they're different ones.
Does that not mean, well, if they're arranged similarly, does that not mean?
They're different. Like I can tell this one apart. This is on the H with Cl. But so grossly, the NMR of this should look. That's the ugliest NMR you're ever going to see. This is intensity. This is parts per million or chemical shift. So grossly, I think I should have 2 peaks. I really apologize. They're so awful here. Admit we can do better. The height of each of these peaks should correspond to 1 hydrogen of each type. So they should be equal in size. And my expectation is if I call this A and this B, that I could actually tell you which one is A and which one is B. Because I know that chlorine is more electronegative than bromine. My expectation is that hydrogen A will be the one that is more shifted, and hydrogen B will be the one that is less shifted.
Hydrogen A would have less electron density.
Right? So it's gonna feel more field. When I feel more fields, the frequency is bigger. The frequency is bigger means the chemical shift is higher. Chemical shift, of course, increases like we read Arabic.
Feel more field like it's like the partner is like more.
Right, Right, so last time we talked about how Brecken was by himself over here, so he feels the full brunt of me, the applied field. You've got all these kids shielding you from my force. So the things that are shielded are over here near zero. The things that feel the full effect of the field are gonna be over here more. As the chlorines suckle electrons away, things are gonna look more like Brecken, they're gonna appear further to the left.
Circles are the only case where it would be AA or BB would be if they're identical.
Yes.
Sounds like a weird.
Chlorine suckles.
Suckle was a bad word, sorry. I came into a conversation that was weird, Amarachi, so give me suckle for a minute and I'll try to do better.
Wait, so chlorine suckles more than bromine? Because
Okay, chlorine is more electronegative than bromine, withdraws more electron density.
And so the thing about the spin coupling, the shorter arrow, is it when it's aligned or opposed?
This is when it's opposed, this is when it's aligned.
If like you get a question on
We
this,
haven't even answered the question yet. This is the old version, this is the new version. So this is the SL, we've reviewed it, now we're gonna do the HL. We ain't even talked about it yet, Audrey.
SL?
Can we like, drop down this? Just not tell anyone, like,
They don't have to know that we passed SL first. Let's just.
Okay, so what's new here? Is that this hydrogen A, that's this one right here, says, yo, hydrogen B can be aligned with or against the field. Consequently, hydrogen A will appear as a doublet because B can be against or with the field.
So hydrogen A can't be with or against the field?
Ooh, Sophia, I was good at suckle, but I didn't hear that.
Wait, so hydrogen A can't be like for or against the field? Like why is it?
Absolutely, it will.
Okay.
Okay, so hydrogen A looks over at hydrogen B is like, yo, you can be with or against, so I shall be split into two. But then hydrogen B looks over at hydrogen A and he's like, yo, you can be with or against. I too shall appear as a doublet. We shall both appear as doublets. A doublet is when you have two equal sized peaks.
Why?
Excellent.
I
Winning.
don't
Yes.
understand how this makes sense.
It just makes sense.
Okay, fine.
Less energy.
Sorry, why does it require less?
Because the field is less big than I thought. There was a big applied field, and now there's a magnet pointing the other way, so it is subtracting from it. So the field you experience is weaker, because this one and this one are destructively interfering. See, I was gonna phone a friend with a math word, I was like, oh, I feel like there's a word there. I don't like destructive interference. I felt like that was a strong, like, cross-curricular link to make this seem more appealing. Okay, let's keep trying.
per molecule, like the hydrogen can only be spin up or spin down. It cannot actually roll. But and on like the NMR, like you showed me, so it's like an average of like elective. That's what we should see two weeks. And like the ratio of like it being spin up and spin down is
That was all good.
So this is a doublet, and this has to, does this have to do with the spin coupling stuff or no?
So this is spin coupling. So A and B are the spins, and they are coupled. A is coupled to B. There is one B. It appears as a doublet. B is coupled to A. There is one A. It appears as a doublet.
And so what are the little peaks? What are the peaks?
So these are the two little peaks. So we're saying at SL, we just have like a woo. And at HL, we're like, no, no. There's still two chemical environments, there's still an integrated intensity of one, but if you really zoom in on that peak, you're gonna see it's made up of two peaks corresponding to his neighbor's hydrogen being either up or down, so two states.
So the DR is less electromagnetic, so it's gonna be more shielded, so it's gonna be on the right,
Yes,
and so the current's gonna be on the left.
perfect.
So, so what are the allowed transitions? Did we not cover that one?
We're only 25 minutes.
Okay, so it's saying that if you have two spins, there are four different ways for those spins to be arranged, right? They can both be down, they can both be up, and then there's two ways for them to be down, up, and up, down. So what is legal in an NMR is to change one of these at a time. So spin 2 can flip, or spin 1 can flip, spin 1 can flip, spin 2 can flip. And so the dotties are always spin 2 flipping, and the solids are always spin 1 flipping. Didn't really help me, but that's why there are 4 lines there.
And so is this the same, does this still correspond to like the aligned and opposed thing?
Does this still correspond to what?
Like the aligned with the field or opposed to the field?
Yes, so that's why there are 2.
So in which, I get that, but in which case, like I know that.
Over here now?
Sorry?
Okay, I don't know where we're going.
No, so you mentioned that, okay, there's two spins, so there's different ways that they can be oriented. But, so does that have to, which one of them is like when one is aligned with the field or when is opposed?
So here, the up is the lowest energy state, and the down is the highest energy state.
So lowest energy is that opposed to the field?
For me, it would be, they didn't show me which way the field is going, so I just took alpha to be up.
So you want to think about that when it comes to doubles? And doubles are when there's like two.
One neighbor is what you're gonna say, one neighbor. If you have one neighbor, you'll appear as a doublet. I promise this seems awful and it gets easy, but we're gonna spend a lot of minutes litigating this, yes?
Wait, why would down be higher energy?
Okay, so there are 4 allowed transitions as seen in the spectrum to the right. I assumed alpha was along the field and beta was opposite the field. That is an assumption I made based on this picture that I stole. I made it when I drew the picture again though, because like I really felt like it was probably true. So the field is going this way.
Oh, okay, never mind then.
So it's just like a graph flipped over?
Okay, let's see. Bad, good. Okay. How many types of hydrogen are there in this beautiful molecule? It's an analog of ethane that has 2 bromines on one hydrogen and 1 bromine on the other hydrogen. There are 2 types. So how many peaks should there be in my NMR? 2. There are 2 chemical environments. Now there is 1 hydrogen of this type and 2 hydrogens of that type. So what would we think about the relative integrated intensities of these 2 peaks, the heights of the peaks?
One of the right is gonna be of higher.
We expect this one to be worth 2 and this one to be worth 1. Frequently to show it in units of hydrogen, they'll put a capital H underneath it. So they're saying you might have to measure something in centimeters. We're gonna look for like a lowest whole number hydrogen atom sort of analog to that. Okay, so we've got most of it, but if you look at this, you're gonna see that you have a doublet. And here, I see 1, 2, 3 peaks. We call that a triplet. So here are my thoughts, Sophia. My thought on the doublet is that I am a hydrogen. Oh, am I the hydrogen? I should be able to figure this out. I'm this hydrogen, right?
I guess.
Because I'm worth 2 H's, and I'm less exposed to the field because I only have 1 bromine, so I should be farther to the right. I feel like there's a lot of reasons that that should be me. So I'm looking over at my neighbor. how many different spins could he have? How many different choices does he have about how he arranges the spins?
How do you restoration of hydrogen?
So that's what I see. I see that I now appear in two places. I am split by my singular neighbor. My neighbor can be up, making the field a little bit stronger. My neighbor can be down, making the field a little bit weaker. I consequently shall appear as a doublet. But if I talk about this hydrogen, he's got two neighbors. Those two neighbors can both be oriented with the field, or they can be down and up and down, or they can be both down. So if we're talking about a net field, this will add to it, this will not change it, and this will subtract from it. How many lines do you expect to see in the spectrum? And what do you expect their intensities to be? 1 to 2 to 1. So I expect to see 3 peaks, 1 to 1. And I expect them to have intensities where these two are short and this one is long. And so you'll see this one is disappointing. It doesn't quite match my expectation, but that's just a sampling error. It's not ever going to be like truly perfect. So this appears as a triplet because it's got two neighbors. This appears as a doublet because it's got one neighbor.
Each line represents the spin of the
Each line represents the amount of energy it takes to flip a spin.
Because like there are 3 lines, but then there's different possibilities because of the spin of the neighbor.
Yes.
Right.
Okay.
So that's how we can differentiate each of the lines.
Yes.
In the previous slide, the doublets were all the same height. Is that the?
Because there's one way of doing this and one way of doing that, so they're equal probabilities. What would we get if we had 4 spins? 3 spins. Let's not go out of our way. Sorry. So can you guys imagine writing down the permutations
No.
of having 3 spins? I don't have 3 spins on my board, so I'm like saying, what would it look like if we had 3 neighbors?
Like 3 different ways.
Okay, so I can have all 3 up.
1 down.
I can have 1 down and 2 up, but I can do that more than one way.
And you have 2 down, but.
2 down and 1 up, but I can do that in a few different ways.
And then all down.
And then all down. Oh my goodness, are there 2 to the 3rd or 8 ways of doing that?
Yeah.
Ooh.
Oh, like the.
Maybe 1, 3, 3, 1.
Is it 1, 3, 3, 1? Have I seen that before in my life?
Stop.
This is Pascal's triangle.
No.
Wait, so that would be 4 different like effects on the. So that would be 4 peaks.
That would be 4 peaks. We call it a quartet.
Mr. Morgan, did you like losing his mind?
He's so ecstatic.
Okay. So we named these with like our biggest nod to Greekness that we can. Triplet, quartet, quintet, sextet, heptet, octet, nonet, who the heck knows et. At some point we just throw in the word multiplet. Multiplet means lots of little peaks. Yo. This is Pascal's triangle in like a real life situation. It's pretty cool. So here's my harder question. Why again did you become a doublet?
Yeah.
Because there's one neighbor. Why would you become a triplet?
2 neighbors.
Why would you become a quartet?
3 neighbors.
Okay, this is not rocket science. We refer to this as the N+1 rule. You will be split by your neighbors into N+1 peaks, where N is the number of your neighbors. So you do not need to draw the spins. You do not need to decide if the field is going this way or that way. You need to have a vague appreciation of Pascal's triangle, vague. And you need to know the N+1 rule, which is not hard for me to say, but it is very hard for you to do. Like, experience shows, like, I can put one box around this and tell you that's how splitting works. And then I'll read things that make me wonder if I was speaking the English when I discussed it. So it's not you, it's clearly me. But let's see if this makes sense. Dibromoethane. 1,1-dibromoethane. Do you agree that there are two types of hydrogens? Okay, if you are this type of hydrogen, how many neighbors do you have? So you should be split into N+1 peaks. And so you should see a quartet, 1 to 3 to 3 to 1. If, on the other hand, you are one of these hydrogens, you see you have a singular neighbor, so how should you be split? Into a double. So the height of this tells me how many of you there are. The splitting of this tells me something about what's next to you in the molecule. That's why this technique is so important. It tells you what's next to you. It tells you how the molecule is actually constructed. Not only do you get information about a set of protons, you get information about what is next to that set of protons. So I know something about their chemical environment, and I know something about what's neighboring them. That if I considered the molecule propanoic acid, I was going to do butanoic, but I don't think I get anything for that extra carbon. Can you all picture propanoic acid? Yeah. I'd like you to draw propanoic acid and its two ester isomers. That would be methyl ethanoate and ethyl methanoate. You're going to try to draw three molecules: propanoic acid, methyl ethanoate, and ethyl methanoate.
Propanoic acid. Prop is 4.
CH3 is a double edge.
CH3 will appear as a doublet because it has one neighbor.
And CH2
I don't remember how to do
It will appear as a quartet because it has three. Three hydrogen. Yes, I'm talking about the hydrogen, and I'm talking about the hydrogen. All good things. Two esters, methyl ethanoate and ethyl methanoate.
methyl ethanoate and ethyl oh my god.
Methyl ethanoate and ethyl methanoate. I don't know which one I said first anymore.
Methyl ethanoate and ethyl methyl
Oh, I'll get them for you.
Is it the prefix, the folder part that's, the part that's connected to the double bond O, or is it the part without?
The single bond O, what it's bonded to is the first word. So if you have the ether O and it has a methyl group on it, you're working with methyl ethanoate. And if you look at the single bonded O, the ether O, if it has 2 carbons on it, you're working with ethyl.
2 carbons to the right?
2 carbons directly attached to the single bonded oxygen. So you should have, in an ester, you have the carbon double bonded to oxygen and you have the oxygen. So I'm saying whatever's attached to that oxygen. If it's one carbon, it's methyl. If it's two carbons, it's ethyl.
Is this methyl ethanol?
Propanoic acid. I don't think I've lied to you yet. I think those things should all be the same. They're all good, right?
Did I switch them? Did I switch them around?
That is correct. So this is my single bonded oxygen. Whatever's bonded to it gives me that first molecule. But that is the only way I can do it. You can come up with your own. Okay, now that you have drawn your three structures, what I'd like you to do is count the number of unique types of hydrogen. So I'd like to know the number of them and how many of them there are.
I'm not gonna explain. Two in the,
Good, no, this is cooler. Do you agree with my structures?
Yes.
Okay. So I'm gonna tell you where I think the hydrogens are. The order of the numbers doesn't matter at all. I'm just reading my molecule from left to right so that you can see some parity between them, but you can write them in descending order, ascending order. And you can tell me I messed up. And unsurprisingly, what you're going to do is you're going to sketch me a high-resolution NMR spectrum of each of these three molecules. So I am providing you with a data booklet so that you may be successful. I think we're going to look at page 26, but it could just as easily be 29. I don't know if you knew this, but we have a Wednesday scheduled today. Crazy. We're so freaked out about the schedule for tomorrow that like the schedule for today never even crossed my mind.
is there a special?
Wait, what's up
Schedule
tomorrow?
tomorrow?
Tomorrow is the mandatory go do things in the world day. So I was looking for rosters and to know where I had to go and
Oh, I chose to stay at school.
I chose the work day, I just don't remember which half of it. Are you going someplace on that one? Which one?
Memorial Herman. Where are you going?
Could you choose where you went?
I could
I
have
chose
stayed,
to
but
stay
really-
here.
I could have stayed, but
You could have stayed, everyone can stay, right?
I know, I just signed up with the,
I wanted to stay here and work on my college.
I really don't know why I went. So do we not have advisory?
We have advisory at the end of the day.
Yeah, it's just an extended
It's
advisory.
a Wednesday schedule. So when you would normally go home at 2:35, you're gonna walk yourself to advisory and question your life choices. Meanwhile, the sophomores will be learning about sex ed, so you can
So after
think that your brother's having perhaps a worse day than you.
Oh, yeah, it's much
And
worse.
that's advisors?
Okay, so one more time, you're looking for page 26 to help you through this process. Page 26 or table 27 is gonna give you where you might expect to find peaks based on the type of hydrogen you're looking at. For example, in butanoic acid, I have this hydrogen here that's clearly on a coup. And so if I scroll down the first page, the fourth from the bottom tells me that a COOH should appear between 9 and 13. I would draw it as 11 because I don't know where it's going to be and I have to draw it somewhere. So again, the fourth from the bottom shows me the H that's bolded is a COO hydrogen. So I'm all about that. These hydrogens are on a carbon that's carbonyl at least, or maybe it's a COO. I like the one that's fourth from the top. It shows a hydrogen on an ester or carboxylic acid functionality. Page 26, I'm looking at the fourth entry down. I felt like these hydrogens should probably appear between 2.0 and 2.5. And the top one is the methyl, and so I expect I'm going to have these hydrogens appearing between 0.9 and 1. And so a low resolution spectrum of this.
Wait, what do you mean by these hydrogens? Oh, no, never mind.
Okay, you're gonna have to screen. So my low resolution spectrum of this would look like that. Have a peak around 1 corresponding to the 3 hydrogens in the methyl group, so it'd be very tall. I'd have a peak around 2 point something corresponding to 2 hydrogens, so it would be the just right soup. And then I would have a peak between 9 and 13, I put it at 11, that's the shortest one. So now I'd like you to take that and turn it into a high resolution. High resolution spectrum. Because you're gonna have 2 more chances, I'm gonna keep working through this problem.
Does it carbon counts as neighbors?
Only hydrogens are neighbors, so I'm looking for hydrogens that are 3 bonds away.
Oh, it's not resolution.
3 bonds is our limit. If you grow up and become a chemist, you can do 5 bonds. Like there's more to this, Audrey, if you want to know more, but all we do is 3. And so I'm going to count these hydrogens have neighbors that are 3 hydrogens away, 3 bonds away. So these 3 see those 2 and become a triplet. These 2 see these 3 and become a quartet. This one doesn't see anything and so stays a singlet. The hydrogen on oxygen is special. It is never split and it does never split.
It can only be like 3 bonds next to it, like.
3 bonds away.
It cannot be like right next to it.
That would be your own type. You cannot be split by your own type of hydrogen. You can only be split by someone else's hydrogen. So you cannot be split by, like if you're this hydrogen, these 2 are your kind. They will not split you. Only different hydrogens will split you.
Like I'm saying like the both next to it.
Only hydrogens are doing this. Only hydrogens have the right kind of energy to affect this. Remember there was a gyromagnetic ratio that said how different fields, like how different things respond to different size fields.
But like what age, like the halogen or
The halogen didn't do anything. It was just the halogen made the 2 hydrogens different from each other. The only purpose of the halogen was to make hydrogen A different from hydrogen B. So the halogens will change where you appear left to right. We know that chlorine will pull you further this way than bromine. And if you have 2 chlorines and I have 1 chlorine, they'll change us because we'll be different from each other. But the role, like, we didn't see the halogens in the picture. The picture is only a picture of what the protons are doing. All we see in this picture is hydrogens. They can be moved left to right by their environment. They can be moved up and down by their number. And now they can be split by their neighboring hydrogens. The halogens, the oxygens do nothing in this picture. It's directly. So this is my final answer to a high resolution picture of this. But what Rami didn't write down, she's working on something else, is that she now knows that, oh, you're good. hydrogen on oxygen is not split and does not split, so it is its own rule. It is because in the solvents, there is always the possibility of hydrogen bonding or proton exchange between the molecule and the solvent. It always behaves kind of wonky.
So it'll always have one peak?
OH will always appear as one peak and it will never split anything else, even if it's 3 bonds away.
Okay.
Always appears as a single peak. So you guys are gonna do these two.
It has to be
So
3
okay.
bonds or less.
Has to be exactly 3.
Or,
And
Because if you're
so
2 bonds away, you're the same type traditionally.
The 3 hydrogen is the tallest because it's shielded the most?
The 3 hydrogen is the tallest because there's the most of them. So this way is how many.
Oh, and then.
This
it's-
way
yeah.
is, do I have all my electrons I want?
So potential question on IB would be draw an NMR based on.
So it easy comes to the sad truth that they will never ask you to draw one. They will only ask you to interpret it.
So,
They're the same problem.
wait, so, would this one have the most difference? Or would this one have the most difference?
Or would they give us an NMR and be like names of all of them?
Yes, that's exactly what they're gonna do.
Wait, Dr. Hennessy?
Yes.
For methyl ethanoate, which group of hydrogens would have the most shielding then? Like, would it be the one that's attached to the oxygen, or like?
So if you were to check your data booklet, table 27, page 26, you're gonna see that 1, 2, 3, 4, 5 from the bottom. You see where hydrogens on the ether side of a Q are. And 4th from the top, you're gonna see where hydrogens on the carbonyl side of a Q are.
Oh, okay. I see. So, let's go here. So this one, frequency of 458. This one here, because it looks the same. And this one, not this one, would go with this group. Okay. Cool. Yeah. A single inch? Where's a single inch? Oh, that's a single inch? Oh, no. No, isn't that, is that a single inch? Apple methylene? Let me map out the. So we have voltage here.
Are we still struggling?
Thinking.
Oh, we just got a reminder, it's a Wednesday schedule. Just in case you didn't know.
Okay, okay. So for methyl ethanoate, this one has 3 peaks.
we don't pronounce the H in H. Like to the point where we even spell the letter differently.
Maybe.
So we spell H like this,
Why would you,
H, but like the other people call it H.
I was not aware that H was spelled like.
Or head.
H.
If you're brown.
You're brown at Maybe.
I have a question.
I am ready for anything.
So in the, at Fulton I believe, going with the 1:2 ratio,
Yeah.
where would you find the H that is only bonded to the C double?
Why, of course, that's because this table is 2 pages long. So if you didn't find your aldehyde, you remember, haha, the aldehyde's on the 2nd page because we hate you.
That is so.
I did not.
Isn't it terrible? I mean, it's like the meanest thing ever,
They could just like format it and just squeeze it to more.
right? So I lied. It's
There's space below.
Exactly, they could just squeeze everything up.
Or you could like count the space.
They could have done a lot of things to make this less awful, and they didn't.
They laughed when they made this data.
So what was this one?
It's the same,
Same one as the other.
yeah.
Except there's only this.
And the values you put on the x-axis, is it just like round, like estimating?
Yes, I'm totally estimating. Again, the IB is never going to ask me to have this skill. They're only going to ask me to interpret things. So I'm just putting something that's in the range so we can compare answers, but I'm not going to bicker about it.
Wait.
Yes.
So how would you tell how many neighbors a certain type of hydrogen has again?
So again, they have to be 3 bonds away and they have to be different.
Okay.
So here I showed you what 3 bonds away was because I could do it with my red pen. Here there are no hydrogens 1, 2, 3 bonds away. There are no hydrogens 1, 2, 3 bonds away. So these will appear as singlets. But
Okay.
here, while this guy's by himself, because 1, 2, 3 bonds doesn't get me to an H, one more time, that ethyl group is going to appear as a triplet and a quartet next to each other. So that is definitely going to be a pattern that we see a lot. The triplet next to the quartet is everyone's little hint, yo, I've got an ethyl.
So is it just to look for like a little, dot sheet, and that's how you know if it's which one is a double or H?
So this guy is going to see these 2 and appears a triplet. This guy, do it up here. This guy is going to see these 3 and appears a quartet. These 3 are going to see these 2 and appears a triplet.
Oh.
These 3 will be a triplet with intensity 3. These 2 will be a quartet with intensity 2. The intensity tells you how many hydrogens of this type, and the quartet says n minus 1, 3 hydrogen neighbors.
Wasn't it n+1?
And, okay, yes, it's the n plus 1 rule, sorry.
So the two, wait, so how would it be a quartet then?
Because there are 3 here, so I have to n plus 1. I was trying to 4 minus 1 to get 3, but like you totally caught me, right? So there's a quartet, so I have to take 4 minus 1 to get 3, because n plus 1 is 4.
And then the other one's a triplet because it's 2 + 1.
Yes. Like I didn't lie, I just never should have said n. I wasn't trying to lie. So natural. This is supposed to be real data. I have 3 molecules that are C3H8O. In the interest of trying to make this as big as I can, I'm just going to write that little note over here. And so I've looked at the spectra, and I've tried to write in something hopefully you can see what I observed. So this here is a doublet at a shift of about 1 with an intensity of 6. This here is a singlet at about 2 with an intensity of 1. And this here looked like 7 to me. Peak was at 4, intensity was 1. So hopefully you can see all 8 hydrogens are here. There are 8 hydrogens. Similarly, we should see 3, 2, 1, 2. That's 8 hydrogens. Tried to show you the location and the splitting. If it's not clear, I'd like you to think about what the 3 isomers are of propanol and see if we can match the isomers of propanol to the 3 spectra.
Where did the 4 and the methylethanoate come
The 4 in methylethanoate came from these 2 hydrogens that are neighbors to the ether side of a kook.
from? The one with the 2-3, the one with the 3-to-3 ratio.
Oh.
Or that ethyl, sorry.
Okay, it comes from the 3 hydrogens on the ether side of the. So if I'm looking at my table, 4 from the bottom, no, 5 from the bottom. I have hydrogens on a carbon on the ether side of an O, appear between 3.7 and 4.8.
The 3.7.
Yes, that's what this type of hydrogen is. And the other side is hydrogens on the carbonyl side, and those are from the top, the 4th one down, 2.0 to 2 point something.
But doesn't it have 3 hydrogens on the thing that you?
It doesn't matter. It's hydrogens of that type. So there could be 2 there, there could be 3 there, there could be 1 there. What it's attached to can be another carbon or a hydrogen. It hasn't shown you what that attachment is.
So it just matters what side of the carbon one?
Yes. That's my propanol problem going. I'd like you to draw 3 isomers of propanol and match them to the 3 spectra. Your homework is butanol, should you wonder. I feel like this is going to be really leading.
The 2 and 3
3. I think one of them won't be an alcohol. I assume it's going to be what I would call ethyl methyl ether and you would call methoxyethane. An O with a methyl group and an ethyl group. So per what Audrey's telling me, I feel like you can put the carbons and oxygens in those 3 patterns. I think you can have 1 propanol, 2 propanol, and you can go for it and have methoxyethane. And honestly, that's probably enough to tell them apart.
What molecule is this?
All of these molecules are isomers of propan-1-ol.
Propane 1-ol.
So how many unique types of hydrogen are there in propan-1-ol?
I would use, there's
3, 4.
I get 4.
unique.
I expect there to be a 3 to 2 to 2 to 1 ratio. 3, 2, 2, 1. How about an isopropyl alcohol or propan-2-ol? 6 to 1 to 1. There are 3 types. And then in the ether, how many did you find? 3. But they have very different ratios this time. Now they're 3 to 2 to 3. So it seems to me that just by virtue of drawing the molecules, we probably can tell which is which. So here, this is pretty compelling for the ether, 3, 2, 3. This is pretty compelling for the 1 propanol, and the 6 to 1 to 1 is what we expect for the 2 propanol. Does it make sense that the 6 appear as a doublet?
Why is it a 6 and not 3, 3?
Because they're the same, both methyl groups are attached to the same carbon, so the methyl groups are are the same, and so the hydrogens on the methyl groups are the same. So hopefully, if we think about this, I'm just gonna draw one bond in. 1, 2, 3 bonds away, I have a single hydrogen. That single hydrogen can be up or down, and so all 6 of those have a single neighbor, so all 6 of those should appear as a doublet. But this hydrogen, how many neighbors does he have?
The top one?
Yes, the top one.
It
6.
has,
So it should appear as a sextet, a septet, a 7-et. This guy will always appear as a singlet because OH is stubborn. He does not split and he is not split. So we again would expect a doublet, a lot of them, and a singlet. Here, how should these 3 hydrogens look? Are there any hydrogens that are 3 bonds away from them? No. So these guys should appear as a singlet. Will they be more shifted at a higher chemical shift or a lower chemical shift than the other methyl group? Higher shift, further to the left, or closer to the oxygen. But these 3 will also be split because they have neighbors. How will these 3 appear? A triplet. And the 2 in the middle have 3 neighbors, so they'll appear as a quartet. So I expect, reading from left to right, to get triplet, singlet, quartet. And hopefully that's what I have, triplet, singlet, quartet.
Says 3.
Where is the quartet in my picture?
Yeah,
Yes, ma'am.
or that picture.
These two see those 3, so they appear as a quartet. Really thought you wanted to see it in the actual graph. Like, okay. Miracles. Why does this have to be so hard? So this is the only one we haven't talked about. You're gonna notice that I use the word multiplet here. How many neighbors does this guy have?
1, 2, 3, 4, 5.
5 neighbors, so we might expect it to appear as 6, but it doesn't have to because the neighbors on the left are different from the neighbors on the right, something we haven't experienced here. And so because the neighbors are different, all we can say is that we expect this to be, split up a lot, and that's traditionally where we use the word multiplet. It means the splitting is complicated, it's not due to a single type of neighbor, and so consequently we can't really tell you what it is. So if you have 2 types of neighbors, we expect to see the splitting. You can see it here, it's all sorts of crazy, but it's not gonna perfectly follow Pascal's triangle because the size of the coupling will be slightly different because the neighbors are slightly different. So this should appear as a singlet because OH always does. This should appear as a triplet because he's got 2 neighbors. This should appear as a triplet because he's got 2 neighbors. And this should appear as a hot mess multiplet because he's got 5 neighbors but of 2 different types. Really, just a little too optimistic. Okay, I have a molecule in mind, and I have the percentages of carbon, hydrogen, and oxygen, of course. So that's easy to get. It's also not very interesting. I'll tell you, I don't know if I care what they are. And so I did the hokey pokey while you guys were working on the last problem, and I tried to figure out how many carbons and everything it had. And by my count, it had 9 carbons, 10 hydrogens, 1 oxygen. So if you'll believe that I did that step correctly.
Is that mass percent?
These are mass percents, and I think I found you the empirical formula. I don't think I've made a mistake in my head, but I was like trying to think about that while we were doing something else. Can you guys tell me what the IHD is of that compound?
What's the IHD again?
It's the index of hydrogen deficiency, of course.
It's like the equation, the two.
It's the number of high bonds.
There's 9 carbons times 2
Okay, I'm gonna take 9 times 2,
18 plus 2,
20,
then minus 10.
10,
Over 2, that's
5. So what does it have in it?
5 double bonds.
Has a benzene.
Has a benzene.
I know this has a benzene and another double bond.
It's bigger than 4, right?
This has a benzene because it's bigger than 4. That's the only way I'm gonna get a ring and 3 bonds 4 in something I understand. So I know there's a benzene. That is the only practical use of IHD right there. Oh my God, why could the functional group speak? In the mass spectrum, I found 3 peaks that I thought I could understand. Please help me to do so. In the IR, there was only 1 peak I thought I could understand. Feel free to let me know what you think that is. In the NMR, you know, it's gonna take me a second. So you're thinking about the mass spectrum, you're trying to come up with the ions that give those 3 peaks. So much more fun when you all do it at the same time. Is it too easy or too hard? I'd like to know what the 3 peaks in the mass spectrum are. I didn't think you got anything by seeing that picture.
The 3 peaks, based on those numbers.
Yes?
Those numbers.
Those are the mass to charge ratios.
Is the parent peak the 134?
Yes, ma'am, the parent peak is 134. Let's make sure she's not wrong. I take 9 times 12, that's 108, 118, 134. I love it. Here what I've done is I've lost 29, and here what I've done is maybe lost 28. I hate that, but I don't recognize this number, which is 34, and 23, which is 57.
We always do it from the parent.
We always do it from the parent peak, but you know, again, because I was trying to math while you guys were working on something else, I don't know the 57 number. And so when I don't know, sometimes I'm willing to try something else, or you know, Karthika can just show me what that is, if she knows already. So Karthika like stole our thunder and said that she knew there was a benzene because of that IHD. And so even though she didn't recognize the loss of 28 or 57 particularly, because those aren't numbers we see, and even though Mohab is like, we don't do that, and I was like, I don't know what else to do, 77 should be in that data booklet. It is just the benzyl, the phenyl fragment.
28's in there and 29's in there, but not.
Right. So 28 should be a loss of a CO, and 29 should be a loss of an ethyl or a CHO. So what are we gonna write down for 105? Okay, so it could be C8H9 plus, or
Or it could be
C7H5O plus. So I've tried subtract C2H5 and I've tried to subtract CHO. You guys were I can't do arithmetic class, so like I'm nervous now. In the IR, I see evidence of a peak at 1690. 1690 isn't something I strongly associate with a peak. What, pray tell, should I do? You have a table, it's table like 26. Yeah, you don't have to guess, like you own the table. Page. Oh no, it is a strong peak. Strong peak. It's at 1690 centimeters to the minus 1. You're looking at table 26 on page 25.
It says medium. It doesn't fall in one and even bigger, but it's close.
Yeah, so it doesn't really jive with any of the peaks, but it's closest to what?
The 1700 band of the.
So you might recall that the frequency is equal to the strength of the bond divided by the mass. Why would it make sense that this is appearing at slightly lower energy or frequency? Is there something about this molecule that's unusual for us? The benzene, the mass is really big. And so because of that benzene fragment, we're not getting it at 1700 where we expected. It shifted a little bit to the lower side because of that mass, but I'm with you guys. I believe that we have a carbonyl bond. Really wish that I could just project this. I don't know why I can't, let's be honest. Are you starting to construct this molecule? Do you have a sense of what it is? Can you draw a CHO or a molecule that contains an ethyl group and a benzene that's consistent with the data you have? Can you imagine that we're going to discriminate between those structures using the NMR? Are you not excited to see this NMR? In the NMR,
Isn't it class
class is over. In the NMR, you see evidence of the ethyl. You just see that pair of a quartet next to a triplet that we associate so strongly with an ethyl. So between losing 29 and seeing that pairing, you know it's the ethyl. Have a good Wednesday, Tuesday, Wednesday. They make me extra cranky. You okay, Dixie?
Yes.